Um, the second group of uh, common mistakes that are going to happen um, are related to a trade-off between the number of experiments you plan to do versus how accurately you can predict a trend based on the experiments. There are three concepts in this category that are very related to each other. The simple one factor at a time design of experiments, or a full factorial design of the experiment that comes into picture here, factorial design, we will call it. And, and what is related to the first one is ignoring the interactions between variables. So in order to understand these very well, I would like us to start first with the simple design of an experiment. And the way I explain it is, I want to go back to my whiteboard. And let's say we want to see, and this is based on the concept of experimentation that we called replication, that we want to see how the strength of a composite depends on the temperature of curing that varies between 100 degrees and 200 degrees C, and how 200 degrees C, and duration of curing that can vary between 1 and 5 hours. So these are, 5 hours. These are our factors. These are temperature and time are our factors. And let's say we measure everything very accurately. The first concept is the simple design of experiments, which is not the right way to do things, but it's a way that can come to mind very easily. And so it's something that we have to address it. Let's say I break down this guy into 4 or 6 levels, into 4 levels. I say 100, 130, 160, and 200. And I divide this into, the times I consider is 2 hours, 1 hour, 3 hours, and 5 hours. So in all, I have 4 cases here and 3 cases here. That gives me 12 possible cases, right? Like, let's say 100 degrees and 1 hour, 100 degrees, 3 hours, 100 degrees, 5 hours, 130 degrees, 1 hour, 3 hours, 5 hours, 160, 135, 200 degrees, 135. So that's 12 cases. But when we talk about simple design of experiments and one at a time, what one may do is, we may say, you know what I'm going to do? I am going to consider first 3 different cases. I say 100 degrees and 1 hour, then 100 degrees and 3 hours, then 100 degrees and 5 hours. So in this case, in this first row of experiment, the number of experiments I'm doing is pretty much just 3, because I have 3 different times here. I've kept the temperature as a control variable. And I measure the strength of each of these 3. And for instance, let's say I get that, in this case, the strength is the highest. So here is 120 megapascal. This is 150 megapascal, and this is 140 megapascal. So I may naively say, perhaps then 3 hours is the best, because here I kept 100 the same, and the hour was the only variable that was changing, 3 was the same. So then I say, now let's go back and fix the 3 and change the experiment. Change the experiment, how? Well, I do 100 and 1 hour, 3 hours. I said I do 130 and 3 hours, I do 160 and 3 hours, and I do 100, 200 and 3 hours. So the number of experiments that I have to do here now is basically 3 more. Because I am going to replicate this guy here. So the results of this is still here. So I need to add 3 more, or a total of 6 experiments has to be done here. So basically, the number of experiments will be 1 plus 3 minus 1 for this case, plus, or I'm sorry, it's going to be 3 plus 4 minus 1, which is equal to 6. The equation of that is in your slides, which is exactly the same as this in parametric form. Now, the problem with this approach is that what if temperature and time are correlated with each other? And for instance, and let's say in this case, when we do the experiment, we realize that this guy is giving us the best case. In this case, the strength is 170 megapascal, which is larger than anything else. The problem is with this approach is that, for instance, we never got to experiment 160 and 5 hours. Although the 3 hours is the best for 100 degrees, maybe at 160 degrees, you need to, if you heat it up to 5 hours, you can get a strength of 180 megapascal. So basically, this one step at a time does not allow you to control all the parameter space, all these combinations, the 12 combinations, and because it ignores the fact that the best condition at a certain temperature that happens at a certain time, at a different temperature may happen at a different time. They could be correlated with each other. And so this is the simple design of the experiment. So now if you go back to the presentation, the number of cases will be this. So in the test we dealt with, so we had K was equal to 2 number of factors, time and temperature. In one case, N1, which was temperature, we had 4. In the other case, which was time, we had 3. So the experiment, sum from 1 to 2, N minus 1 will be the 6 that we got before. So in each case, N is the number of different levels of each factor that we consider. And level is nothing fancy here. Level is basically, these are 4 levels of temperature, 3 levels of time. And so another example is in the context of aerodynamics, that you are trying to, for instance, find the best combination of wings for optimal flight conditions. And again, you have to consider the interaction between factors. So the number of experiments is very few compared to other factorial cases that we study. So here what we're doing is actually we're testing one factor at a time. So we set T, check the time, then we check time, we fix time, check the T. So T and time. So for instance, in a matrix format, if these are the cases of temperature and time is here, what we have to do is we have to test each case. That is 100 degrees, 1 hour. 130, 1 hour. 160, 1 hour. 200, 1 hour. 200, and all of these 12 cases. But what we did in this case is we went from, oops, is that we went from here, and then we found the maximum, and then, I'm sorry, we first fixed the temperature, we went from here, then we fixed the time, we went here. So what we ignored in all of them, which is dangerous, is these other cases that we didn't test. So let's stop the video and we will continue in the next video.